Hello and welcome to Career Talk by Shubham Pathak, and this is the lecture 3 of the series of electronic devices for GATE. Today we talk about equilibrium carrier concentration. So for understanding this concept, first we need to know what is the hole and electron concept, right? So in a semiconductor, let's say we take it silicon semiconductor, okay? We have electrons and we have holes. Now what is hole? Let me introduce you. Let me tell you what is hole. See, this is a 2D grid. Okay. These are atoms. Okay. Silicon atoms. And it having 4 electrons. Right. I am denoting electrons by cross. Similarly, it has 4 electrons. In its outermost shell, it has 4 electrons. Similarly, it is an atom, it has 4 electrons in its outermost shell. Okay. These electrons are loosely bounded with their parent atom. Loosely bonded with their parent atom. So, energy required to make them free will not be much. Okay, will not be much. So, at T is equals to 0 Kelvin, right, there will be no external energy available to the semiconductor. So if no external energy, no external thermal energy is available, then all electrons are bonded. These are loosely bonded, but they are bonded with their parent atom. Now if temperature increases, semiconductor starts getting thermal energy. This thermal energy is provided to electrons. These electrons take up the energy, and if that energy exceeds the energy which is required to break the bond between that electron and its parent atom. Okay, see, if it is an atom, this is electron which is bonded with some force, some energy, right? This energy will not be much. These are loosely bonded electrons in their outermost shell. Okay, so if energy, thermal energy, TH लिख सकता हूँ यहाँ पर, which is equals to KT. You know that KT is Boltzmann constant. Boltzmann constant. So if at T is at temperature equals to T Kelvin, the thermal energy would be KT. So if KT increases, that energy, let's say it is EB, E bond energy, yani the energy which is required to break the bond between the parent atom and its electron. So as ETH is greater than EB, then this bond will be broken. And as soon as this bond is broken, your electron will be free from its parent atom. It can freely move within its atom, right? It is free from its parent atom. So if it gets disconnected from its parent atom, it leaves a vacancy behind it. It leaves a vacancy behind it. Let me show you. Okay, so if that is a bond, bond breaks out, then it leaves a hole here and electron is freed, right? Now there are other electrons as well. I am just showing electrons for the simplicity of the diagram. This is electron, this is electron, this is electron. So this electron will fill up this vacancy. Now as soon as this electron fills up that vacancy, it leaves vacancy here, right? So vacancy will be created here. Now if that electron fills that vacancy, new vacancy created here. So what you can see is these bonded electrons are also moving, right? Bonded electrons are moving. Bonded electrons are moving. But they cannot move uninterruptedly. यानी ये बिना किसी रेस्ट्रिक्शन के मूव नहीं कर सकते अपनी मर्जी से. जब इलेक्ट्रॉन अपने पेरेंट एटम से फ्री हो गया तो इट कैन मूव फ्रीली विद इन दैट एटम, राइट, विदाउट एनी रेस्ट्रिक्शंस. बट दीज बॉन्डेड एटम्स आर बाउंड टू द रेस्ट्रिक्शंस और द अवेलेबिलिटी ऑफ द वैकेंसी. यानी जब वैकेंसी क्रिएट होगा उसके विसिनिटी में, उसके करीब में, तभी वो वहां पर मूव कर सकता है. So these bonded electrons are also moving but restricted. It is a restricted movement. Okay. So what we can observe here that this negative charge, electron has a negative charge, you all know. So if this negative charge is moving with this pathway, this is the pathway, right? On the other hand, we can see that holes, these vacancies are moving this way, right? And if electron has negative charge and neutrality principle, you know that, then these holes must be having equal positive charge. So we can observe that holes are moving with same speed as bonded electrons, right? With same speed as bonded electrons. Bonded electrons की स्पीड से ही exactly opposite direction में मूव कर रहे हैं होल्स in opposite direction. So for the convenience and secondly, first for convenience and secondly to distinguish the movement of free electrons and bonded electrons, we say these movement of holes. So the naming holes is hypothetical, but the movement of hole is not hypothetical. That's why we used to consider it in our calculations, right? ये दिमाग में सवाल आ सकता है स्टूडेंट्स के कि अगर होल एक हाइपोथेटिकल कंसेप्ट है जो कि यूजुअली सुनते हैं, तो उसकी कैलकुलेशन, उसके मूवमेंट को कैलकुलेशन में, एग्जैक्ट कैलकुलेशन में यूज क्यों करते हैं? सो दैट इज द रीजन दैट इट कि होल नेमिंग नॉमेनक्लेचर इज हाइपोथेटिकल, बट the movement is exactly happening between the bonded electrons. So that movement of bonded electrons has to take into consideration, and that's why for our convenience and to distinguish between the movement of free electrons and bonded electrons, we said that bonded electron movement can be considered as a movement of holes just in opposite direction, right? So we know that the holes are moving in the opposite direction as of bonded electrons. So it is very convenient for us to use in our calculations, right? So these are electrons and holes. So one thing you can also notice from that कि as soon as electron get free, a free electron generated, a free hole is also generated, right? So number of number of electrons should be equal to, must be equal to number of holes. ये बात हो रही है इंट्रिंसिक सेमीकंडक्टर की. I am talking about intrinsic semiconductor, that is there will be no impurity yet. Okay, so at T is equals to 0 Kelvin, at T equals to 0 Kelvin, there will be no external energy, so number of electrons equal to 0 and number of holes must also be equal to 0. But at T is equals to some, let's say 300, for example 300 Kelvin, then E must be some number. Let's say I would say it a number of electrons E and holes will be number of holes, right? लेकिन हमको ये बात पता है कि किसी भी टेम्परेचर पर फॉर इंट्रिंसिक सेमीकंडक्टर नंबर ऑफ इलेक्ट्रॉन्स शुड बी इक्वल टू नंबर ऑफ होल्स, क्योंकि नंबर होल्स का जनरेशन ही जब ये होगा जब इलेक्ट्रॉन का जनरेशन, फ्री इलेक्ट्रॉन का जनरेशन होगा. यहाँ पर इलेक्ट्रॉन का मतलब आप फ्री इलेक्ट्रॉन से समझ रहे हैं, राइट? क्योंकि फ्री इलेक्ट्रॉन को बोल दिया गया इलेक्ट्रॉन और बॉन्डेड इलेक्ट्रॉन को बोल दिया हमने होल, राइट? सो Ne इज इक्वल्स टू NH, जिसको कन्वीनियंस के बोल दिया हमने कैरियर कंसंट्रेशन ऑफ इंट्रिंसिक सेमीकंडक्टर, I फॉर इंट्रिंसिक, carrier concentration of intrinsic semiconductor. Okay, so after this, now when we talk about intrinsic semiconductor at equilibrium means thermal equilibrium, yani it could be at any temperature, these values will be different but constant, right? At certain temperature there will be fixed number of electrons and holes for certain specific intrinsic semiconductor. Okay, next, so there is a law of mass action, right? We need to understand this for understanding equilibrium electronic concentration, equilibrium concentration, right? So before this you must be knowing what is doping. Doping is adding impurities to intrinsic semiconductor, right? To intrinsic semiconductor. So let's say I have a silicon atom. Okay, another silicon atom. Electrons. Right? So there will be another silicon atom here. And so on, right? So these are silicon atoms, right? Now if we replace this silicon atom with some impurity, right? With some impurity, if I replace this, okay, yes, okay. So if I replace this with arsenide, okay, so arsenide has 5 electrons in its outermost shell, 5 electrons. So 4 electrons get bonded with 4 electrons of nearby silicon atoms, but there will be 1 electron left which is not bonded to any of the silicon atom, right? Which is not left. So, but this electron is loosely bonded with its parent atom. Loosely bonded to arsenic, यानी its parent atom. Its parent atom से loosely bonded है, so it require very less energy to get free from arsenic, right? Let's say E is equals to kT. So at certain temperature K, at certain temperature T. So if that kT energy is sufficient to make that electron free from its parent atom, but that energy, that is E is less than the bond energy. Bond energy of what? Silicon bond energy. Silicon bond, right? इससे कम है तो there will be only one free electron is generated. Only one free electron is generated. No hole yet. Okay? No hole is there. So what we can say? We can say that electron concentration, Ne, will not be equal to hole concentration in semiconductor due to डोपिंग. ठीक है, ये होता है. अब डोपिंग कैसे होती है, वी विल टॉक अबाउट दिस इन लेटर क्लासेस, राइट? लेकिन बेसिक्स इज, if you doped it, if you replace it, how do we replace practically? We will talk about it later. So if we replace it with an atom, so there will be more number of electrons than holes. Ne would be greater than NH. अब देखिए, ऐसा तो है नहीं कि एक ही सिलिकॉन एटम को रिप्लेस करेंगे. एक क्रिस्टल के अंदर, एक सिलिकॉन सेमीकंडक्टर के अंदर बहुत सारे एटम्स को, सिलिकॉन एटम्स को हम रिप्लेस कर देते हैं. फॉर एग्जांपल लेट्स से आर्सेनिक, हम थर्ड ग्रुप के एलिमेंट से भी रिप्लेस कर सकते हैं, यानी गैलियम से भी रिप्लेस कर सकते हैं. लेट्स से अगर आर्सेनिक से रिप्लेस कर देते हैं तो जो बहुत कम अमाउंट का एनर्जी है, जो कि सिलिकॉन की बॉन्ड एनर्जी से कम है, लेकिन आर्सेनिक के लूजली बॉन्डेड इलेक्ट्रॉन को उसके पेरेंट एटम से फ्री करने के लिए काफी है. उस एनर्जी की वजह से नंबर ऑफ इलेक्ट्रॉन्स जो जनरेट होगा, दैट विल बी वेरी हायर देन द नंबर ऑफ होल्स इन दैट सेमीकंडक्टर. सो दिस कंसंट्रेशन is not balanced now. So we talk about now extrinsic semiconductor, right? Extrinsic semiconductor, let's talk about its concentration, equilibrium concentration. So at certain temperature T is equals to T Kelvin, T1 Kelvin, temperature is equals to T1 Kelvin, there will be majority carrier concentration and there will be minority carrier concentration, right? So what is majority? जिसका concentration, जिसका नंबर ज्यादा होगा. minority वो जिसका नंबर कम होगा. तो अगर मेरा इलेक्ट्रॉन का concentration ज्यादा रहा होल के concentration से, राइट? तो मैं इसको बोलूंगा n टाइप सेमीकंडक्टर. एन मतलब आप नेगेटिव से समझ सकते हैं, इट इज अ नेगेटिव टाइप सेमीकंडक्टर. नेगेटिव से आप ये मतलब समझ सकते हैं कि देयर विल बी मोर नंबर ऑफ इलेक्ट्रॉन्स, राइट? और अगर मेरे पास इलेक्ट्रॉन का कंसंट्रेशन कम रहे होल के कंसंट्रेशन से, तो मैं इसको बोलूंगा पी टाइप, यानी पॉजिटिव टाइप सेमीकंडक्टर, राइट? यानी देयर विल बी मोर नंबर ऑफ होल्स देन इलेक्ट्रॉन कॉन्सेंट्रेशन, राइट? सो these are two types of semiconductors, n type semiconductor and p-type semiconductor. So for concentration, according to mass action law, right? number of electrons into number of holes will be equal to Ni square, right? In general, we can write it as Np equal to Ni square, right? So this is law of mass action. ठीक है, mass action law एक ही बात है. Law of mass action in which electron concentration into hole concentration will be equal to the square of intrinsic electronic concentration or carrier concentration of that intrinsic semiconductor, right? So this is the equilibrium carrier concentration of extrinsic semiconductor. So we can say that, let's say if we are talking about n type, right? So n will be greater than p. So अगर मैं बात करूं तो माइनॉरिटी कैरियर कंसंट्रेशन क्या होगा? माइनॉरिटी कैरियर कंसंट्रेशन दैट विल बी इक्वल टू उस सेमीकंडक्टर का इंट्रिंसिक कैरियर कंसंट्रेशन का होल स्क्वायर डिवाइडेड बाय उसका मेजॉरिटी कैरियर concentration. So I hope you have understood the electronic equilibrium carrier concentration. We are saying it carrier because there are two types of carrier, that is electrons and holes. And in the next lecture we will talk about the electron hole pair generation and its effective masses and further energy band model, etc. So thank you very much. And in the end of this video, if you like the video, then do share it, subscribe the channel. Thank you very much.